Chapter 27 Notes, Atom Models. In the late 1800s, the model of the atom consisted of a random distribution of positive and negative charges. They called this the plum pudding model. Then in the early 1900s, Ernest Rutherford did his gold leaf experiment, which you know all about and can draw pictures of, hopefully. And the main things of his experiment were to show that most of an atom is empty space, with a small nucleus in the center and a small electron orbiting around. This is Bohr's model. He combined the ideas of Rutherford, Planck, Einstein, and atomic spectra. This is what we're going to be looking at the next couple days. The atomic spectrum, every atom has a different spectrum. The picture here is showing a gas inside of a tube. If we shine white light through the gas, there's certain colors of that rainbow that are absorbed, and we see a spectrum with dark lines in it. It's called an absorption spectrum or a dark line spectrum. If we take that same gas and zap it with electricity, that's what this device is doing. It gives off those same colors that it absorbed. And every different atom, every different element has its own unique characteristic pattern because they all have different electron configurations. So Bohr's model is the standard one we use for chemistry. We have protons, neutrons in the center. We have the electrons on different shells. A K shell can have 2 electrons. The L shell can have 8 electrons, and so forth. This is Bohr's model. Now in physics, we're only looking at these. They call them energy levels. Instead of drawing the whole circle, we're just looking at each line. And instead of calling them shells, we call them energy levels. He said that electrons can only exist in certain allowed orbital states. We call them energy states, and he's able to calculate the radius of each one of those orbits and the energy of each one of these orbits. And these are the two formulas for doing so. N is the energy level, and Z is the atomic number. All right, so for the energy level, the bottom level is this inside K shell. So that would be energy level 1, and then the L shell is energy level 2, and the next one is energy level 3, and so forth. So this is the energy level diagram. So this is energy level 1. They call it the ground state. For a hydrogen atom, the electron is on the bottom orbital level, the K shell, and this is called the ground state. This is where its electron would be. This is showing where the other electron shells would be if we had extra electrons there. Now, just like the photoelectric effect, we can shine in a photon of just the right amount of energy. This is the energy of this first energy level. This is the energy needed to release the electron from its energy level. And if it's this amount of energy or more, we can kick off that electron. If we give it more than 13.6, the extra energy goes into kinetic energy, just like on the photoelectric effect. Although we have to be careful not to use the photoelectric effect formula on these problems because it's not photoelectric effect. This electron is sitting on the second energy level, level number 2. It has an energy of 3.4 electron volts. This would be like the L shell. And if we hit that one with a photon of this energy, 3.4 electron volts, we can also eject it off of the atom. So now let's look at if I take this electron and hit it with a different amount of energy. 10.2 electron volts happens to be the difference between the energy of the first level and the energy of the second level. 10.2 electron volts is exactly the energy difference, and if I hit it with that frequency or that energy of photon, I can make that electron jump to the second orbital. This is going from the K shell to the L shell. Now for a hydrogen atom, that electron is supposed to be in the bottom level. If it's moved up a level, it has extra energy. It has 10.2 EVs extra energy. We call that an excited state. And it's going to hold on to this energy for a random amount of time, just like the carbon dioxide molecule is holding on to the energy from the sun. Because it absorbed this frequency of light, that rainbow is going to be missing that color. So let's say we shine an entire spectrum of white light on this. This one color is going to be absorbed to jump that electron up, and we're going to be missing that color out of the rainbow. So this electron is going to stay on this orbital shell for a random amount of time, and then when it jumps back down, it's going to give off that exact same amount of energy because that's how much energy that electron was holding. In this case, it's going to give off that same color that it absorbed before. That's where the emission spectrum comes from. Electrons jumping down makes an emission. Electrons jumping up makes the dark line spectrum. So this is the formula that we use to calculate. This is the difference between the two energy levels, and this is the wavelength of the color that's being absorbed for the electron transition. Now I said every atom has its own electron configuration, therefore every atom has its own spectrum of colors that it absorbs or gives off when you zap it with electricity. This is a drawing for a hydrogen atom. This is all the possible transitions, jumping between all the different possible levels. And these different transitions, each one would make a different color of light, and all of those colors of light make up this pattern. Some of those are in infrared, some of them are in ultraviolet, some of them are in the visible range. So Bohr's model explained how all of these transitions and energies work, but he didn't explain why. And we have one more model of the atom to look at that explains about all of this. And this is de Broglie's model. He looked at Einstein's theory that said photons have momentum, and these photoelectric effect and this energy level diagrams are showing that we have momentum and collisions going on where the photons are acting like particles. So de Broglie said if waves can act like particles, well then particles can act like waves. And the only particles light enough to do that would be electrons. And sure enough, he was right. If we remember Young's double slit experiment, we shined light through double slit, and you expect to see the light go straight through and make two bright spots. Instead, we got an interference pattern. It turns out the exact same thing happens with electrons. If we send electrons through a double slit, we get the same interference pattern, which means the electrons, the particles, are actually acting like waves. This is the diagrams when we were studying waves. We called these standing waves, and these were the drawings we did in our notes of a vibrating string showing the different waves it can vibrate. The lowest vibrational state was called the fundamental frequency, or the first harmonic. And then there were multiples. We can double the first harmonic, we can triple the first harmonic, we can quadruple it to get the next harmonics. This whole thing was called the harmonic series. And Bohr made a new model of the atom based on the harmonic series. So here I drew out the orbitals for each one of his orbits, and in the middle, when we have one electron, we have one wave. The next one, the larger radius, we have two wavelengths. The next orbital has three wavelengths, and all of those go together to make our orbital shells. The next one, I've laid those out flat so you can see how this works. Each wave can only be a certain wavelength, otherwise it's going to destructively interfere with itself. So let's look at just the middle one here. If I fold it over on its end, just at the right length, this would be just the right radius of the orbit, my electron can follow its complete wave all the way around the path. Now if I change the radius just a little bit, now these waves are going to interfere with each other and cancel each other out, and we will have no electrons will be able to exist on these smaller radius orbits until we get to the next one that's just the right radius where the wave can add together all the way around its orbit again. So de Broglie took Einstein's formula that said a wavelength of light can have momentum, and he turned it around and said, well, a particle like an electron can have a wavelength. So this is called the de Broglie wavelength, and we put in the mass of an electron, and electrons, they have to be moving at a fairly fast speed in order for this to work, and it acts like a wave, and we can calculate the wavelength of an electron. This is a drawing I got from the textbook showing that the wavelengths need to be exactly the right length with the radius to add together to make a complete wave. If it's not a complete wave, it will destroy or destructively interfere with itself. End of notes.